on the presentation part. Let me just minimize this and let me maximize this. Wonderful. So now that we have started, so I'm going to talk about on the quantitative microscopy, using electron backscatter diffraction, and I will just touch upon Kikuchi transmission, Kikuchi diffraction. But the major focus is going to be, I want to get my laser pointer. Yeah, laser pointer is here. Will be on electron backscatter diffraction. So electron backscatter diffraction nowadays is no longer a technique which was as exotic when I started some 20 years ago. It has become a very routine technique. But what we will try to do is to see how we can use electron backscatter diffraction in a very, very effective manner. That is the purpose of this lecture, which I will try to wrap up in say around 45-50 minutes, so that we can have the last 10 minutes for discussion. And in my lecture also, I am not going to just keep on, giving gyan to you people for the next 50 minutes. We'll make it a little interactive. So with this in mind, let us move ahead. So the most important point that I want everyone to focus on is that even before we use any characterization technique, be it EBSD or transmission Kikuchi diffraction, or tomorrow something else, precision electron diffraction, what we should really focus is like, what is the principle? And this information should be known. So we should know what are the limitations of our technique that we are using. And also how far we can go and what can be done. And there may be techniques which are much simpler that can solve the problem. So we should be really aware of these things. So therefore, I say that choice of proper characterization tool, we should know things about microstructure. Why? Because if I'm having a big casting, I know that my grain size will be in tens to hundreds of micron. And then if I'm using a TM for that, it does not serve the purpose, right? But yes, if there are precipitates, if this is an aluminum alloy, a cast aluminum alloy, where there may be some precipitates, then yes, I need to do TM. If, why I say that you should not be doing this is that, you are aware of this story. In Kanpur, we are aware of this story that, there is this king or a prince whose bodyguard is a monkey. And then what happens once the prince is sleeping and there is a fly that is disturbing the prince? And then can any one of you, the students over there, can complete the story? What happens? The fly sits on the nose of the prince. And then what happens? Does anyone know?
Yes, sir.
What happens? You tell me.
The chops off the head.
No, he does not chop off the head, but it's not that brutal a story. But he uses a sword, right? A sword to shoo off the fly. And in the process ends up removing, kind of chopping off the nose. So in Hindi, there is a saying, na, naak kat gayi, right? Naak kat gayi, and you got insulted. So that is what happens with, most of the PhD students, because every PhD student, wants to show, I am using a better technique. I am using EBSD. I am using TM, I am using TKD, I am using PD, I am using HRTM, I am using 4D STEM. Yes, sir, but you see what is required for you, right? And therefore, we have to know that there are two kinds of information that microstructure carries. One is the information in the real space, the microstructure and all that you see, and the other one is in the reciprocal space. And there are, situations like if you want to determine the precise lattice parameter, or if you want to get the global dislocation density, reciprocal, like techniques which are based on reciprocal space, like X-ray diffraction, the humble X-ray diffraction, which does not give you any colorful images, can give you very good precise lattice parameter value, right? So we should appreciate not just the real space, what we see in the microstructure, but also the reciprocal space that is in X-ray diffraction. Now, what makes EBSD and TM stand out is that you can get the information of the real space, the compositional space, and the reciprocal space with different levels of accuracy and resolution from the same region of the microstructure. So that is the power of EBSD or TKD or precision electron diffraction. So we should be, kind of armed with this information, that what are the advantages of the technique that we are going to use. So it gives you information from the real space, from the reciprocal space, and if you stick in an EDS detector from the compositional space from the same region. But at the same time, you know that when I talk about real space, I am getting information whether from SE or BSE. So now again, let me ask you this question. If you are doing simple imaging using a scanning electron microscope, you can get at least two kinds of image. What are the two kinds of images? Tell me. Some other student should answer now. What are the two kinds of images that we can get in a scanning electron microscope?
Sir, band contrast and
अरे बाबा एसीएम का सवाल पूछा है हमने. आप तो you have mucked up the answer for EBSD. I am talking about simple scanning electron microscope. What are the kinds of images that we can get in a scanning electron microscope? अरे बाकी जनता सो गई क्या? We have to do SEM, right? We have to do EBSD. We have to first learn SEM. बताइए SEM में what all images, what all detectors you have in a simple scanning electron microscope? See, if we do not have our fundas pakka na, then we cannot. It's like making a building, you know, with the foundation very weak, and we want to live on the Burj Khalifa, you know, 10 story, 100 story. That entire bridge will collapse, or building will collapse, right?
Nilesh?
So please tell me what are the different kinds of electron, like images that we can get in a scanning electron microscope? Okay. Have you heard about secondary electron image and backscatter electron image?
Actually, Nilesh, can you hear me?
People, are you there? We have to make it interactive, right? I am not going to blabber for the next 45 minutes.
yes, sir, yes, sir.
Secondary electron and backscatter electron.
Hello.
So the spatial resolution
Yes.
of secondary electron image and backscatter electron image, which
Nilesh.
is better?
माइक इज म्यूट. उनका तो ऑन है. ओके. कैन यू हियर मी, नीलेश? हेलो नीलेश.
Professor Vishwas, I am able to hear you.
गुस्सा नहीं है. He is able to hear you. Okay. Nilesh, we would like to see you.
Yeah, you can see me also, but I don't have very good light, and if I'm using my phone, so well, I'm not that photogenic. So
Yeah, you are quite photogenic to us. Okay. Actually,
Okay.
the volume of the mic was not too good. Okay, so I corrected it. Now I think
Okay.
they can say something. Do you want to say something? Yes?
The other two images are AC and BSE images.
Yes, very good. Now you tell me from like where, you know, which has a better spatial resolution. So we all agree that the secondary electron image has a better spatial resolution than backscatter electron image, because the secondary electrons are coming from the top 50 to 500 angstrom, and the backscatter electrons are coming from about a micron, 1 micron to 5 micron, that kind of a, you know, depth, right? They are coming from a larger volume. So see, even in very good papers and all, you will find that people write SEM image. Now, there is nothing like a SEM image. We need to say that this is a secondary electron image. This is a backscatter electron image. And that is why we need to worry about, you know, what is the resolution, what is the accuracy, and so on and so forth. Only when we have understood our, you know, scanning electron microscopy in details, then we can go, you know, to electron backscatter diffraction or transmission ki kuch diffraction. So, but as I said it, for any characterization techniques, the first 4 points remain equally valid, that we should really know the basic principle. That is what we should do. Fine. So moving on, I talked about diffraction. Why do we go about diffraction? So let me just go back to the physics that we studied in school. Again, you tell me, what do I have here? I can see these kind of fringes, and here you can see, what do I have here? I have two apertures through which if I pass light, I get fringes. This is which experiment? We have all done this in 11th standard and 12th standard. What is this experiment known as? The students can answer now if you remember what you were doing in 11th and 12th standard.
Double slit
Double
experiment.
slit experiment.
Yes, Young's double slit experiment. And here you see the beauty, you can see the beauty of reciprocal space. These two, kind of apertures that I have, they are horizontal. So look at the pattern on the screen. It is vertical. Now, instead of these two apertures being horizontal, if I were to make them vertical, what will happen to these this pattern? Can anyone tell me?
Those will become horizontal.
Excellent. So that tells you about orthogonality. So the reciprocal space, this is nothing but the reciprocal space. It is orthogonal. Now, instead of, and then the next thing that I try to do, what will happen if I keep it horizontal only, but if I bring them closer, what will happen to the pattern? You tell, can someone comment? If I keep them horizontal only or vertical only, and if I bring them closer, what will happen to the pattern? Will the pattern remain the same or will it change?
Pattern become wider.
The pattern will become wider.
Yeah, it will become wider. Very good. So see, again, reciprocity and orthogonality. Reciprocity and orthogonality. This is a characteristic. So now, if you go, so instead of just two patterns, if you have multiple patterns, on my cardboard and I put light, I get a checkered pattern. Just like we wear a checkered shirt, you will get a checkered pattern. Now, replace your light with X-rays, electrons at very high energy, 200 kV, accelerated at 200 kV in a TM, and replace these apertures with atoms, and you can get, or a column of atoms, and what you can get in 3D, a 2D projection of, a phenomena which is very similar to what we saw in interference, right? And you get the so-called diffraction pattern, right, in a TM, right? So you are seeing the reciprocal space. And this is very, very important, right? So this is the genesis, right? Like you are seeing the real space as well as the reciprocal space. But what happens in EBSD? When I talk about diffraction, we know Bragg law, lambda, or Bragg equation rather, lambda is equal to 2d sine theta. But when you talk about electrons, be it in a, say, a TM, which operates at 200 kV, or when we are talking about electron backscatter diffraction at 20 or 25 kV, it's not just diffraction as one event, a single event. It's a multiple event, right? So not our Bragg law in reciprocal space and all. Reciprocity that I talked about, I have just written the Bragg's law. You see, it is like, 1 over d and 2 over lambda for n equal to 1. So right hand side, you have in the reciprocal space. So, but that's fine. But what I'm trying to say is that this is like for X-rays, where your X-ray undergoes, or X-ray photon undergoes one scattering event. Your electrons have a lot of energy. So what happens is that they undergo multiple scattering events. Remember, lambda is equal to 2d sine theta only once. But here, you undergo multiple scattering events. And because of that, we get what is known as dynamical diffraction. So all the structure factor calculation and all we have done goes for a toss. Diffraction is very, very easy, right? When we are doing electron diffraction, unlike in X-ray, right? So now I talked about TM and all. Why EBSD is so powerful, and I'm sure Professor, David Field must have touched upon, is that if you have, a thicker sample in a TM, it undergoes inelastic, inelastic scattering, and you end up getting these Kikuchi bands, which can be linked with your crystallography, right? I'm not going to go in details. These crystallographic the maps, the Kikuchi bands, can be correlated with your crystallographic orientation. Now, for that, so when you are going to use a technique like EBSD, remember that, I know that I'm going to look at these bands, but I have to look at, I need to know what material, what symmetry, what point group symmetry, what is the space group, where the atoms are located, right? If I do not have this information, then, EBSD is useless. Nowadays, a lot of people are working on, different kinds of, alloys like high entropy alloys or different newly developed alloys. So you can't simply put copper, aluminum, titanium. You can't do like that, right? So, why? Because you should have done the homework first. Homework first means you should have done the X-ray diffraction first, so that you know the information. You should know information about the chemistry. You should know the crystal structure. You should roughly know the lattice parameter. All this information has to be fed into EBSD so that, these bands can be, kind of correctly indexed. You can, kind of attach them to a particular orientation of, say, a copper crystal, or say a brass crystal. There is nothing like a brass crystal, right? So it's a copper zinc solid solution. So now, how do I index it using my, using a copper file? There is no foil for brass. That brass file is nothing but for your, the beta brass, right? Like it's like the ordered B2 structure. But how do you do for solid solution? Everyone knows what is a solid solution, right? A substitutional solid solution, or there is an interstitial solid solution, right? If I'm getting two phase, steels, a FCC phase and a BCC phase, what should I do? If I'm having, say, DP steel, which has ferrite and martensite phase, what are the phases that I put? All this information you should know a priori before you, even start collecting your data. And this information will not be given by the operator over there. This has to be given by you, the person who is doing research. And I'm very unpopular at IIT Kanpur amongst the PG students, because I tell them that, you are so much interested. Kanpur is known for all chaat and all. So like when you go to chaat or to eat, pani puri, you tell, put this much of hari chutney, this much of lal chutney, give me this much of, sweet water, this much of, tangy water. But you care about your chat, but you don't care about your own research, right? That should not be the case. That should not be the case. You should do all our homework and then sit on the microscope. So this information as a user, because this is a SPARC program, most of you will be going back and then collecting data, doing EBSD, TKD, and use this information to further your research. So if your beginning itself is not proper, it is not based on sound foundations, it will not be proper. So please work on that. All this information and is available. So see, this school itself, the first lecture was by Professor David Field, who talked about crystallography, because that is the genesis of it. So we should know all these things before we go and sit on the microscope. So once you have these patterns, remember these patterns. So if you look at the principle of EBSD, as I said, lambda is equal to 2d sine theta. Now you would say, how do you calculate lambda? For 20 kV, how do we calculate lambda in electron microscope? Can anyone comment on it? How do we do the calculation? Again, we have to go back to 12th standard physics. Please tell me, how do we calculate it? How do we calculate the wavelength of an electron accelerated by a certain voltage? Does anyone remember? There is a particular term about it. What is this wavelength I'm talking about?
Lambda
De
equals
Broglie wavelength.
Which wavelength?
De Broglie wavelength.
De Broglie wavelength. And remember, for this you don't do the relativistic correction, because your velocity is not very high, not approaching that of light. But for 200 kV, if you do a TEM course, there you have to do the correlation. So now, if your lambda is very large, very small, of the order of fraction of a picometer, your D is lattice parameter is of the order of angstrom. So imagine that your Ewald sphere is much larger, right? So you are taking sections. So also your theta is going to be very small. So if theta is very small, then the semicone angle of that cone that you are getting is going to be very large. Therefore, these bands that n lambda is equal to 2d sine theta that I showed you earlier, look at this. These are going to be, this angle is very small. So this cone, I am showing you 2D image, but in 3D you can rotate it about the axis, about the vertical axis. You get a cone. Your diffraction cones are having very large diameter, like the ones you are seeing over here, and you get this pattern. And this pattern can be linked with the orientation. In good old days, when Professor Field and Professor Stewart, right, they used to manually index and find out what is the orientation. Now everything can be automated. You can easily take, thousands of frames per second now, right? And you can move really fast and index. So you can collect a lot of data. So, nowadays people talk about big data and, machine learning and all. See, this is one technique where we were having lots and lots of data. But if you don't collect the data in the correct way, or if we are not aware of how to use the data, what are the problems that we are getting, right? You may be collecting data on one machine and doing analysis using another software. If we do not maintain the frame of reference and all, we will end up getting, there is a term in, all these computational materials engineering, people talk about garbage in and garbage out. You will get some images, some EBSD data, Many students get that for all different calculation techniques. And then a job of a PhD student should not be to generate data to make 2 or 4 slides for the weekly meeting. The purpose of our research is not to just make, prepare, slides for the weekly research meeting. The purpose is to solve a problem, right? The purpose is to solve a problem, and solving it correctly is important. So remember, the pattern, the Kikuchi pattern is linked with your crystal orientation, and that in EBSD, we are collecting a data pixel by pixel. So you have to tell the step size, right? Okay, I want to scan this much area. I want this pixel by, this much. So how do you choose the pixel size? The pixel size has to be chosen in such a manner that your grain size is much larger than the pixel size. So you can't have a situation that your grain size is 100 micron and pixel size is 100 nanometer. So if you were to scan, say, say 2 millimeter by 2 millimeter region, it will take you ages. Right? You can't do that. Your beam stability may not be there for your microscope, right? So there you have to see that what is the realistic, pixel size that you are choosing, so that your grain boundaries do not appear stepped, but at the same time, you do not have, too many pixels, unnecessary data. You are like overdoing it, right? So all this information you have to think even before you sit on the microscope. Nowadays, what happens is people go, give the sample, collect something, the TA or the wherever you have sent the sample, some data will come, and then we scratch our head and try to find out, some sense, try to make some sense out of it. I hope that after doing this SPARC course, that is not the case happening with you, right? That is what has to be our idea, that if we have reached the goal, right? So therefore, we should worry about things like resolution, things like accuracy, things like precision, and things like sensitivity. We may not be talking about precision and sensitivity, not relevant, for our EBSD, but resolution and accuracy, right? And remember, as I told you, in EBSD, you can get information, yes, about the real microstructure, right? What is the grain size and all. So we need to worry about what is the smallest grain size. Here I'm looking at a grain. I'm not looking at a pixel. Just Baba, this is a grain. This pixel has, or this region of the microstructure has this orientation, right? So what is the resolution, right? In terms of spatial resolution, what is the smallest grain size that I can resolve? That is the spatial resolution of EBSD. So someone working on nano nickel, who is depositing nano nickel by electrodeposition and getting a grain size of 20 nanometer, cannot do EBSD. You should be aware of that, because that is not the spatial, that is well below the spatial resolution of electron backscatter diffraction. At the same time, if I'm going to talk about a subgrain, where the difference between the orientation is like 1 degree, 1.5 degree, I can't do that. I may do that in a TM, but in EBSD, my angular resolution is 1 degree, right? Similarly, I cannot determine elastic strains in EBSD. Why? I cannot do that because, again, my accuracy of, all these measurement that I'm doing from Kikuchi band, the orientation and all, is not as great. So these things we should be aware, and only then we should venture into, into doing EBSD. Otherwise, remember, my dear friends, you may be able to, solve a short-term problem. If you get a supervisor like me, you won't be able to go around and show something on a weekly meeting. But you will be found out either while, when your thesis is being written, or you submit a paper and paper comes back with a very nasty review saying that, oh, you have not even covered the basics. So we should keep in mind that we keep our fundamentals very, very strong. Only then we can build up and move forward, right? So now, since now I am coming to the basic, right? Like the quantification. So yes, EBSD can generate beautiful images. It gives you colorful images. But not only that, in this case, in addition to colorful image that you are seeing, I have also imposed a grayscale. This grayscale is the image quality that tells you what is the quality of the image, the diffraction pattern that you are getting. Now, you can imagine that when you go to grain boundaries or when you go to subgrains, right? That is where at the grain boundary, the beam is falling in 2 grains. So you have 2 different, patterns from 2 different grains. So what is going to happen? The quality of the pattern is going to be poor. At the same time, within a grain, if there are defects like dislocations and all, or like the dislocations can form low angle grain boundaries, subgrain boundaries and all, you are going to have, the diffraction quality will not be good. So see this image, what you are having. It appears like somewhere like kind of an optical image that has been, colored. So in optical also you can take an image and you color. This appears like that, but this is not like, this is IF steel sample. Long back, probably the first sample that Professor Somjit Biswas had done EBSD on, and he was kind enough to give me his data that I am showing you. So you can see very nicely so much of such a rich information that is there. You can get the defect information here. You can get the crystallographic information, like as in which color, and you can get the information in terms of what is like elongated grains and also the morphology, right? So all this information you are getting in this one image, and that is why EBSD has become so powerful in the last 20-25 years, right? Now here, from single phase material, if you move to two-phase material, again, you get an image, called as the image, a map called as the image quality. Here there are two phases. This looks like an optical micrograph, right? Optical micrograph. Again, this image was taken long back. This is Ashkar's sample when I was a student way back in 2006-07. We took this image. So you can see, an image that looks like an optical micrograph. The right image, the middle image rather, is the phase map. And then on the right-hand image is the orientation map. So all this information you can get using EBSD. So if you want to show your professor that, oh, I am working so hard, you can just generate, some kind of, 20 images from the same microstructure. But now you have to learn, understand, and explain. So see, I can easily find out what is the phase fraction here. I can find out plenty of, information from one simple scan. This scan earlier used to take 4-5 hours. Now these scans can be easily done, in less than 1 hour, with the modern EBSD systems, right? So all this information can get. And as we say, a picture is worth 1,000 words. But it's not just about a picture. You have to get quantitative things out of it. So let me show you a few more beautiful images. Very large area also. You can go now in millimeter square. Easily you can go. But at the same time, you can index multiple phases. It's not like only one phase or two phase. You can index 3, 4, 5. There is no limit. But you should be aware what is the ground truth. What kind of symmetry? There comes the option of pseudo symmetry. Now, when to use it? Many people do not know that. Like if you are working on soldiers and all, you will have tin. Tin is a body center tetragonal phase, right? So when to use pseudo symmetry? You should be aware of that. That's why the knowledge of crystallography and all is important. So please do the homework, then sit on the microscope. Otherwise, it is like garbage in and garbage out. And this is something that has to be avoided. So I have spent almost half an hour, if not half an hour, 25 minutes to just emphasize that, how important it is, what you have to do before you go to the microscope, right? Now I will tell you that what all you get from the microscope, right? I'm not done yet. I have to add one more thing. But once you get the data from the microscope, what all you are supposed to do, right? So now, yeah, in situ EBSD and all also can be done. So those things I won't talk about. So you can see, you can do so many things. In situ or ex situ deform, look at the same region and all. The wealth of information that you can get is tremendous, right? So please keep this in mind. So now I just want to touch upon this. And this thing that I'm talking about is transmission Kikuchi diffraction. So unlike electron backscatter diffraction, where, you are in the kind of, the electrons are getting reflected back, here you are in the transmission mode. And again, what is the funda? Why do I go to transmission Kikuchi diffraction? Look at the interaction volume. Look at the interaction volume. Where, in which case? So you have to tell me in which case. This is EBSD on the left hand side, on the right hand side it is TKD. In which case the interaction volume is lower? Tell me, my dear friends.
Transmitted electrons.
Interaction volume is smaller in case of EBSD or in case of TKD?
TKD.
TKD. So in which case your spatial resolution is going to be better?
TKD.
TKD. So keep this in mind, that why we go from EB. You can do what all we do in EBSD can be done by TKD, right? But TKD gives you a much better spatial resolution, right? So what is spatial resolution decided by? If I want, I can give a step size of 1 nanometer also. Who stops me? But then you have to see what is the spot size. So you remember, in a scanning electron microscope, when I talk about a spot size, you have to first worry about, when the first time you do focusing of your, the electrons after it comes out of the source, right? So there, what is the spot size in a normal hot short key? It is of the order of 25 to 30 nanometer. So using a step size below 25 to 30 nanometer in EBSD mode is of no use. In TKD, yes, in TKD you can use a step size of 5 nanometer. Don't do that. If you read a paper and say, I saw this colorful image and there was a step size of 5 nanometer, then for EBSD also I will use a step size of 5 nanometer. Arey sir, that 5 nanometer step size was for TKD. There it is valid. Why it is valid? Because your interaction volume is so smaller, right? Why? Because if you look at the size of the interaction volume, the sample is electron transparent. So the sample thickness itself is lower than the interaction volume that you would have had. So in TKD, you can take a step size of 5 nanometer or 10 nanometer. In EBSD, you cannot. You should not. It will be just again garbage, right? So please keep this in mind, right? So this is what we have to keep in mind. I'll just touch upon another technique which is called electron channeling contrast imaging, and that can give you again very nice information. But then you can just take the information about the defects, about dislocations, about twins, and then take this information. I won't talk about it in details, but take this information to your ImageJ software and all and quantify. You can also determine dislocation density, twin fraction, twin volume fraction, stacking volume, the probability or the frequency of stacking faults and all these things you can determine by combining simple EBSD is, ECCI is like coupled with EBSD. And then once you get it, simple image analysis tools and all, you can utilize and get this done. So I will just touch upon it in the last 5 minutes of my lecture. But now let us come down to quantitative. So once I give you a sample, where will you do EBSD? You tell me. If I give you a rolled sheet, where will you do EBSD? A rolled sheet, by the way, so we know that EBSD we do on surface, right? So a rolled sheet has, ND, RD, TD, right? What is ND, RD, TD? ND is normal direction, RD is rolling direction, and TD is transverse direction. So when I say ND plane, it is actually the RD-TD plane, like, one direction is RD, one direction is TD, and the ND direction is coming out. So you tell me, let us talk in terms of the plane, in terms of plane normal. So you have ND plane, RD plane, and TD plane, right? The ND plane, RD plane, TD plane. On which plane will you do EBSD, my dear friends? Can anyone comment on it?
RD&D.
See, your supervisor cannot come to work with you to tell कि अरे ये sample को ऐसा रखिए और EBSD कीजिए. You have to take the decision.
RD&D plane.
RD&D.
Anyone working on? Please.
RD&D.
RD&D plane.
RD&D plane means TD plane. The answer is absolutely correct. Why is it so? The answer is absolutely correct. You will look on the TD plane, which contains the RD direction and the ND direction. So the answer is EBSD is a microscopy tool. So I also want to see what happens to the, to the grains, how the morphology is changing and all. So in rolling, what happens? In rolling, so let me go to that slide where I have my rolled sample. I'll go this later. In rolling, what happens? Your grains are compressed along the ND and they get elongated along the RD. While the grain, technically speaking, along the sample thickness, the sample width is not changing, isn't it? That is why we call rolling as plane strain deformation, right? As plane strain deformation, right? So remember, you want to look at that. But how do you represent texture? The texture is to be represented, which is improperly, represented here. The texture is represented in terms of the ND frame of reference. Why? Because conventionally, when you do pole figure measurement and all, ND is at the center, RD and TD make the X and Y axis. So when I was told that I have to give this presentation in front of, for a SPARC, I just got hold of my, the youngest student, Aditi, who has just joined. She has not even done my texture course. So I just told you these pole figures, she has done one thing very correctly. Look at the order of pole figures she has given. What are the pole figures she has given? This is for a FCC high entropy alloy. She has given 111, 200, and 220. And this is something that I really like what Aditi has done very, very correctly. Why? You tell me, because if you do FCC and X-ray diffraction, the first peak is going to be 111, 200, and 220, right? So this order she has maintained. Where she has mistaken is that she has taken this on the TD plane. She has forgotten to bring it down. This is not her data. She has collected from her senior, and she tried to plot it. So she plotted along the TD plane. So again, the frame of reference is important. So suppose you are supposed to do, say, compression. So compression, you can define only one axis, right? So in that case, on which plane will you do? Compression, everyone knows now. Everyone knows what we do in compression. I have a good dabba here. So I will take a, this looks like a cylinder to everyone, right? Now I'm going to compress, right? So this thing gets compressed. Now you tell me, where will I do EBSD? On which face will I do EBSD? How will I cut my sample so that I get a plane and I will do EBSD? Please tell me, my dear friends. I can tell you that I have infinite options.
So
But it is
basically we have to see the reference according to the compression axis. So basically we have to dissect the sample in between, and then
you have to dissect, because you want in the plane, the compression axis should be contained in the plane. Yes or no?
Yeah.
Should be contained in the plane.
Yeah.
So see, I have just talked about two techniques. If you go and look at what Professor Biswas had done, he worked on, ECAP, equal channel angular pressing. Or nowadays, you people work on additive manufacturing and all. So please be aware of the initial sample direction. Otherwise, we can make mistakes, right? So these are the things that one need to worry about even before you go and sit on the microscope, right? Now, once you have EBSD, now I told you, you can get this colorful image. This is called as inverse pole figure image, because you see this inverse pole figure. This is the kind of fundamental zone of cubic symmetry and RGB we have done. You get these three images. Only one image is valid here, right? So that is what you can choose. So people use it for generating these images, then the black and white images. Then another thing for which people use EBSD, very, very common. I have seen in the last 20 years, everyone wants a grain size determine karna hai. If you want to determine the grain size, life is tough. Because why? You have to prepare optical microscopy, then you have to use image software, use a horizontal intercept or vertical intercept. People are lazy. They feel, let us use EBSD. I will do EBSD, the scan will come, then I will press a button and I will get, this is your average grain size. And I will get a standard deviation. My job is saved. I don't have to do anything, right? Anyways, I just polish the sample roughly. I have to give it to an operator. He or she will do electropolishing or vibromet. And then another operator will do EBSD. This is like research outsourced, like parenting outsourced. Research is your baby. Okay, if you do your baby, you guys are much younger to have a baby, but if your baby is taken care by the nanny, when the baby grows up, the baby is not going to remember you. Baby will not call mommy or daddy. The baby will call nanny. Those will be the first words of the baby. So remember that your research cannot be done by the technician. Your research has to be done by you, right? So grain size will come. So what we will do is, let us try to determine the grain size. So I am giving you what has happened. I noticed that, this thing got stretched. Oh my God, I'm going forward. Let me go backward. So let's assume this is not looking like a square because, the slides got stretched. But if I give you a square, so let's assume, so let me move ahead. I don't want to cover this. Let us consider a square. Draw a square. The student should draw a square and the square is of side A, right? Both the sides are A because that is why it is a square. Please do that in your copies. People who are virtually present also can take a copy. SPARC presentation or online presentations are just not to mark your attendance, right? By being there and doing other things. The only advantage we have is that we can wear probably a half pant, and or not wear the shoes and attend this. That's the only luxury you have. So draw a square. Now let us consider that this is my micrograph and divide it into 4 equal parts. And these are like your grains, right? So you have 4 grains in this micrograph of size A into A. So now let me ask you the question. What is the grain size here? Can anyone tell me? You have 4 grains now. What is the grain size here? Bataiye bhai, someone else should answer. I am seeing that only one student is answering. Others can also answer. People who are available online, all they have to do is switch on the microphone and answer my question. I think I'm ruining my reputation as a popular teacher in the country, but yeah, I think you have to be strict also. बताइए, what would be the grain size? Online जनता.
A by 2.
A by 2. But what is that grain size? Average grain size means what? Is it area average or number average? Do you know what is area average and what is number average grain size? बताइए, बाकी लोगों से भी you can consult. This is not a quiz. This is not an exam. It is not me versus you. It is all of us together in this. We are all learning, right? We are all learning.
So,
बताइए,
so what
number
what-
average
what
क्या
is-
होता है?
What is number average?
So let
what
us
is
go
area
back to
average?
the slide that Aditi made. Number average grain size. So our Aditi has written a formula. You see, what is it? What she has written? Number average. Number average is what? Summation di. I goes from 1 to n divided by 1 over n. Right? This is number average. What is area average? Summation I is equal to 1 to n ai di divided by summation ai. Got it? ये formula लिख लीजिए भाई आप लोग. Please write down the formula. Right? You got na? I am also multiplying with the area. Now, let us revisit the problem that I asked you. What is the grain size? And now you tell me what is the grain size. So you tell me for the number average as well as the area average grain size. Our problem we have seen, right? So what is the area of the grain that has, say, like a side of a by 2? A square by 4, that is the area, right? So what will you get? 4 into a by 2 into a square by 4, right? Divided by a square, isn't it? So what is the area average grain size, my dear friend? आपने जो default, what default value you told, a by 2, that was actually the number average. Yes or no? Am I right or wrong? You tell me, students.
Yeah, it's A by 2. For
Right?
number
That
average.
was the number average. What is your area average? Area average is going to be,
2A.
you know that, 4 into a by 2 into a square by 4 divided by a square. What is the value that you get, my dear friends?
2A.
2a कैसे आएगा भाई? a by 2 आना चाहिए. 2a कैसे आएगा?
A by 2.
एरिया एवरेज ग्रेन साइज कितना है? आप बताइए भैया, फिर से कीजिए. अरे बाबा, do 1 by 1. a by 2 into a square by 4. This is ai di term. Agreed with me or not? di is a by 2, ai is a square by 4. Yes or no? So what is ai into di? That is a by 2 into a square by 4. That is a cube by 8. Agreed with me or not? एक grain के लिए it is a cube by 8. How many such grains you have? 4. So a cube by 8 plus a cube by 8, you have to do 4 times. That is 4 into a cube by 8 means a cube by 2. That is in the numerator. In the denominator, what do you have? Summation of all the 4 grains that you have. So the area of one grain is a square by 4. So a square by 4 plus a square by 4, you 4 times. That is like nothing but a square by 4 into 4. You get a square, right? So what did you have? You had a cube by 2 in the numerator divided by a square. What are you left with, my dear friends? A by 2. So in this case, my number average and area average grain size is a by 2. Did everyone get this or not? बताइए भाई. ऑनलाइन जनता. I can see my former student, Professor Vivek Sahu here. So he can comment
sir.
that I have made
We
myself
got it.
very unpopular if his students are also attending, but
Sir,
that's
I
fine.
have a doubt in the nomenclature of grain size. Should we take the diagonal or the side?
So why are you taking diagonal? You should take the side, right? Why diagonal? See, again, if you are fitting it as an ellipse and all, you don't complicate things. Nah? When I say grain size, I'm going to simply apply a horizontal intercept or a vertical intercept method. Yes or no? What you are confusing it with is that you are trying to fit. That is what EBSD does, that it tries to fit your grain size as a ellipse, right? And when it fits as an ellipse, there is a major axis and there is a minor axis, and you get an aspect ratio and all. I gave you just a thought problem, a simple thought problem. And that's why I'm saying that, let us revise the basics, right? So simple, if you were to do on this microstructure, if you were to do horizontal or vertical grain size intercept, what is the grain size you are going to get? A by 2, right? Yes or no? Isn't it? And even if you get this measurement, what I'm trying to say is that the way I do averaging, I could do number averaging and area averaging, right? So does everyone agree with me? Everyone is getting an answer A by 2, both number average and area average? All the janta?
Yes, sir. We
Yes,
got
sir.
it.
Fine. Now we will play a small trick. And what is that trick? Now, instead of these 4 grains, I'm going to have 10 grains. How do I get 10 grains? I take any 2 squares and then I divide it into, again 4 grains. So now, how many total number of grains I have here? I have 10 grains here. I have 10 grains here, right? 8 grains. What is the size of that 8 grains? Can anyone tell me? See, the image has got distorted because, I think Aditi had given me in that simple chota wala mode. I made it in landscape mode, so this got expanded. Bataiye bhai, kya hoga? What is 8 grains and what is the grain size, like the size, like just the nominal size? Can you tell me? ये जो छोटा छोटा वाला grain है, the small grains, what is the size of those grains? Can anyone tell me? अरे A by 4 no baba, right? Agree or not? These 8 grains, which are 8 grains, 1, 2, 3, 4, 5, 6, 7, 8. Each grain, if I were to do horizontal or vertical intercept, the size is A by 4. Yes or no?
Yes, sir.
So now in my microstructure, there are 8 grains which have a size of A by 4. And what is the size of the remaining 2 grains?
A by 2.
यहाँ पे आंसर दिया है, वो नहीं दिखाऊंगा.
A by 2.
The size of the 2 grains is A by 2.
A by 2.
So now let us not calculate it, but what will be the number average and area average? You try to figure out. Okay, you try to figure out the number average and area average, right? And you will find out that the area average is a higher value than the number average, right? But area average is a better representation of a microstructure which does not have. So, whenever I talk about averages and all, I am thinking about, nice normal distribution. Only then I can give you a mean and a standard deviation. If you have multimodal distribution, you cannot do that, right? So nowadays, a lot of people are working on heterogeneous microstructure, or in additive, you get lots of kind of, somewhere you get equiax grains, somewhere you get columnar grains. So you have to worry about the aspect ratio, the grain size distributions and all. Remember this. So it's not like one size fit all. My neighbor, my lab mate calculates average grain size, so I'm also going to calculate average grain size. Ye sab nahi karna, right? So we talked about 2 things. Number 1, where to do EBSD. And then you come to the correct frame of reference, right? The step size to be chosen and all. Then the next thing that we use is like grain size, to quote the grain size. So grain size also quoting, Baba, one has to be very, very careful. Very, very careful whether you are quoting area average, number average, vertical intercept, what is the aspect ratio, all these things, all the commercially available and even open source software for EBSD data analysis. Just button dabao and something comes out. It's like don't use it like a black box. They all come with a good help file. Go and look at the help file and read what you are doing. Okay. See, please keep in mind that research is not like organizing your wedding of your cousin or friend. It's not an event management. You are good with your supervisor, you are good with the technicians, you collect all the data and a lot of data is generated and you write a paper and you are done. Your fundamental should be very, very pakka. Otherwise, you will end up getting good papers, but tomorrow when you go out, you will not be able to defend it. So all the fundas, you can't learn this in a lecture of 1 hour, but you can cover all these things, simply by looking at, the help file and, going and looking at lectures. There are very good lectures by, Professor Samajhdar, Professor Suhas, Professor Field, Professor Wright, all these things. And Professor Somjit Biswas also has this entire, set of lectures that he keeps on, on his, portal and on YouTube, right? So please go through that, revise the basics. That will give you a lot of power, right? So now let us go and look at again a high entropy alloy. So apart from a good IPF map, good pole figures, you can get what is known as the misorientation distribution. Misorientation distribution also, you see here, it goes up to 65 degree because it is material with cubic symmetry. If you go to materials with hexagonal symmetry like titanium or magnesium, it goes to 90. Now, why 65 or 62.8 and why 90? The answer lies in crystallography. You should know. Why Mackenzie? What is Mackenzie distribution? And why this boundary? Professor Sumantra Mandal must have talked about this. So, why you are getting this very high boundaries at 60 degree misorientation? Tell me, people, why 60 degree misorientation? The hint lies in, like, you attended Professor Sumantra Mantra's lecture, right? Sumantra, from IIT Kharagpur, Professor Sumantra has given a lecture. So can anyone tell me why this 60 degree peak is coming here? Bataiye bhai, which boundaries are these boundaries?
Sigma 3 CSL boundaries.
Sigma 3, yes, the twin boundaries. Now coherent or incoherent. Now, with these boundaries, how do you determine the grain size? You want the grain size, you see here, the parent and the twin, like the parent grain and the twin grain relationship. Now, do you want, Hall-Page equation? Everyone knows the Hall-Page equation. What is the Hall-Page equation? Tell me. Bataiye. See, I don't want you people to think in silos, like our undergrad students do. Oh, in this semester, I will study physical metallurgy. Next semester, I study mechanical metallurgy. So by the time you go from physical metallurgy to mechanical metallurgy, there is a semester break. In that semester break, they have lost everything. So when you start teaching them, like solid solution strengthening, they have forgotten Human-Authery rules, right? You don't want to be in that situation because, the fundamentals are very important. Tomorrow, when you go in the job market, this is the information that you need. And if you don't have, then you can say that, hey, I have a PhD, but I'm not getting a job. Why is it so? It is because our fundamentals are not pakka. We have to keep the fundamentals pakka. And there is no shame in revisiting. When I'm giving a basic lecture to someone like you, not only I'm giving GAN to you, I am actually revising my own fundamentals, right? So please participate in it. Your juniors are preparing for comprehensive exam. Please participate in it. Help him or her with that. That will also help you, right? So Hall-Page equation, my dear friends, tell me.
D equal to di plus k by root d.
I didn't, root d, but I will write in terms of sigma. So I'll write sigma is equal to sigma naught plus k by square root d. Now, you all know, Professor Sumantra would have talked about it, that the twin boundaries, particularly the coherent twin boundaries, are much better resistant. They offer a much better resistance to your dislocation than a random high angle grain boundary. And that is why you do entire, grain boundary engineering. So can I really use sigma is equal to sigma naught plus k by square root d, even if I am defining a twin as just a grain? No. If I have twins, these annealing twins, I may have a different value of k, or instead of square root d, I may have a different kind of a power to my thickness of the twin, right? So all this information we can get. You click a button in the software, you will get the average grain size. You will get two different grain size. One is like considering twins at grain, and the other considering twins separately. Again, no one cares about it. You click a button and you get output and you feel, okay, I have shown so much of data. I have created 2 slides and I have done it. That is not the purpose. That is not the purpose, right? That is not the purpose. Okay. So this is what we should avoid. You have to read. Ki Baba, when I am doing the grain size, even before we start, you have to tell in the EBSD software how you are defining a grain. Ki what is the misorientation, 12 degree, 15 degree. Go and read papers. Ki okay, by default it is 15 degree. For your material, it may be 12 degree. That may be a better definition. So please read papers. That will give you information. right? So similarly, if you move on, like I showed you this example of rolled, like which plane to look and all, same way. And he's calling undeformed aluminum, but this is not undeformed, this is hot rolled. Why it is hot rolled? Because you see, there are low angle grain boundaries. If it was undeformed, you will not get low angle grain boundaries. Here, no low angle grain boundaries are there because this is fully recrystallized, right? So now you see, after deformation, what happens? The fraction increases even further. The CAM distribution, you see here, spatial CAM map, again a colorful map. What is CAM? What is LAM? ये सब jargon हो जाता है. What is GOS? What is, you should not call it GOS, GAM, GOS, GM. Please read about it. Please read about it. See how people have used it in different papers and all. And that is how we can learn more, right? So all these are all intragranular misorientation. You can get geometrically necessary dislocations and so on and so forth, right? So all this information can be obtained, right? Like as you deform and all, you can see when you lightly deform, you see this extension twin and contraction twin in titanium from the misorientation of the grain boundaries. If you go and deform more, actually, here the twin boundaries are disappearing. No, not because the twinning has reduced, because, the dislocations have gone and the orientation, the kind of the misorientation has changed. Okay, so this is the information that you can get, and there is a lot. So please read papers. And Somjit sir can add that when you are students at ISC, used to look at the recent papers which are coming in good journals like ACTA and other, Nature and Science, and see what all these people are doing, and try to reproduce those kind of figures. So I'm not going to talk about the Taylor axis or intragranular misorientation analysis, or the SMID, the SMID or the Taylor factor analysis, or I'm not going to talk about the Luster-Morris parameter and so on and so forth. I'm not going to talk about the determination of CAM inside the grain and at a random angle grain boundary or at a twin boundary. All these things can be done. Professor Sumutra Mandal does it regularly. All you have to do is write a small program. All these things can be done by you, right? So remember that we can do very advanced things by looking at the recent papers. But our fundas should be pakka. Only then we can move forward. So I won't jump. I will just say that please keep in mind what is your reference system. And, we have to look at that, what microstructural attributes. I talked only about grain boundaries and, GNDs and all, but you can get information about, orientation relationship between two phases. You can get, look at the triple junctions and so on and so forth. You can look at the intragranular misorientation, deviation, and so on and so forth. All this information can be obtained. And the reliability of data, you can complement it with different, so if your CAM is increasing, grain size is reducing, that hardness should increase, right? Or if you do XRD micro strain should increase. All those information you have to keep in mind. And as I said, you have to constantly upgrade your knowledge. Okay, you have to cover the fundamentals also, and at the same time constantly upgrade. So I think I will stop over here because I'm sure Professor Sandeep Ghosh Chaudhary is here. I don't want to take time from his thing, but I will just end it up with showing you just a few images and tell you the power of your SEM. You talk with your SEM vendor, and with some effort you can get TM quality images by combining EBSD with the BSC detector, right? So you can get these kind of images, and then you can do in image and all, you can quantify. These are all twins, martensitic laths, the HCP laths and all that you can get. These are in a high entropy alloy, and you can also do correlative EBSD and ECCI. We do not have a dedicated ECCI system, but still we were able to do it. So if we can do it, anyone else can do it, right? This was done by Swati. So if Swati can do it, anyone else can also do it. So this is the capability that you have. And finally, I will tell you, where do you use TKD? If you really have a high resolution, image at, very low feature size, right? And EBSD is not able to do this. We did with the help of Professor Pradeep at IIT Madras. You see, we are looking at the orientation relationship and all between the FCC gamma and the HCP martensite phase. We could very nicely do it using TKD, and we could also do some TSEM. So you see, at the finer scale also you can do using TKD. So I think I'm going to stop over here, and I would be more than happy to take any questions from you. Fine? Thank you very much.
Thank you so much, Nilesh. Please give a big applaud. So, so it was a very motivating talk actually, and we can means I can see how passionate you are about this research, and we are really grateful that you came here and you actually tried to motivate to the maximum that is possible for a teacher to do, and I am very thankful for that. And I think
No,
that all
pleasure,
of
pleasure indeed is mine. Thanks for the opportunity. Thank you very much.
thank you so much. And I think that the students should give another big applause to you.
No, no, my pleasure. Thank you. Thank you.
So, Nilesh, Professor Field is here, and I actually means we actually are facilitating everyone with a small gift. Okay, it's a small gift which, because you are not coming to IIT Kharagpur any soon, so we'll send it to you by
Oh,
post.
that will be great. Thank you very much. Yeah, it would have been nice. I'm at BRC. It would have been great if I could have come there and meet, Professor Field also.
Yes.
So, Professor Field, hello from my side.
Yes.
I still remember the first workshop I attended at CMU in Icotom, and I was lucky enough to have Professor Field and Stuart Wright Dr. Stuart Wright to teach me. So that was so what all I have shared with the students here. I have learned everything from Professor Field and Professor Stuart Wright and Professor Satyam Suhas for sure. So good to see you, sir, here.
Thanks, Nilesh. Good to see you as well. And I'm motivated to go focus more on fundamentals again. So it was a very motivating talk. So I think that's fantastic.
Yeah, thank you.
And I'll
Thank
motivate
you,
my students like that as well. I like that.
Thank you.
So, thank you, Nilesh. And
Thank you very much. I think Sanjeev sir will be waiting.
Yes.
So thanks for the gift and everything, and thanks for the opportunity.
Thank you,
Professor Vishwas.
Nilesh. Thank you
very
so much.
Thank you.
Take care.
So I
Have a
have to
nice
leave because the BRC people are waiting. Otherwise, I would have continued to hear the talk.
Yes.
So you will have to excuse me. Okay. So Professor Vishwas.
Yes. No issues.
Thank you.
Thank you.
Thank you very much.
Thank you,
Thank
Nilesh.
Thank you.
You may. So I think Professor Arul Kumar is there. Are you there, Arul? Welcome, Professor Arul Kumar Mariappan. So let me introduce.
Hi, can you hear me?
Yeah. Can we see you?
Yeah, but I'm traveling now. It's not a good place because I'm keep on road right now.
Oh.
So I'll just give a talk. Yeah.
Okay. So give me a moment, okay? So Professor Arul Kumar Mariappan is a professor in IIIT DM Kanchipuram. So he has recently come back to India. He was a chief scientist in Los Alamos National Lab, USA, for a long period of time, 15 years, working on continuum mechanics, relationship with texture, doing crystal plasticity simulation, coding, modeling, and let us hear from him microstructure sensitive constitutive equations related related topic, right, Professor Mariappan?
Yep.
Yes. So without any ado, I would like you to continue, take over from me, and start your invited lecture.
Okay, sure.
Yes.
Can you see my screen now? I think
I think we can. So, full screen.
can you see my screen?
Yeah, you're sharing it.
Okay. Yeah, I have to burden with me for internet connection because I'm on road.
Yeah.
Sometimes it goes off a little bit.
Mm-hmm. And we are also sending you a lot of data, right? In terms of video, maybe. Anyway, use the first option anyway. Show my screen anyway.
Yeah, I'm clicking. Yeah.
Yeah.
Yes.
So you yeah.
Next.
তো ওনাকে কি লগ আউট করে লগ ইন করতে বলবো?
Yeah, sure, I'll do that.
Yeah. You can click on show my screen anyway.
Yeah.
Okay. Log out করে log out. হ্যাঁ, ভালোই। I think he is traveling.
Can you see my screen now?
Yes, we can see your screen now entirely perfectly. Yes.
Okay, I'll start from here then. Okay, thank you. Okay.
Thank you.
So good afternoon to everyone, and myself Arun Kumar, and thanks for this great opportunity, and good to see you through video call. That Professor David Field is here. So I'd like to thank Sumit Biswas for giving me an opportunity. So today I'm going to talk about the microsensitive mechanistic constitutive model, and this work is not like one project; it's multiple various projects has been supported me to develop the framework what I'm going to show you. So I like to start with the acknowledgement for that all the financial support starting from India, especially from the USA. Various funding agencies supported me for this work. So maybe I'll just skip this one for some time. I'll start with this one. So we have materials everywhere in our life. So all materials are experiencing a wide range of boundary condition, loading conditions. If I take this simple example, where in which we have a heat exchanger tubes, and if I'm the bottom image, left image, it shows that is this. We'll take it. This image shows how does the stress distribution we may going to have in the heat exchanger, and the right side it shows the temperature distributions. If you look at it, both on mechanically as well as in the environmental point of view, temperature wise, the material is experiencing wide range of boundary conditions. In addition to that, the shape is not that simple. It's really complicated. If I'm going to boil down, we have two issues. Very often we make the components with the complex shapes that leads to significant internal mechanical fields. Second, and also we have a rapidly growing operating conditions and functionality. As a result, what we need, we have to be smart enough to select suitable material. They will design the material. When I say design, not the component level, I'm talking about the architecture of the material microstructure, and we should be able to tell us how to fabricate the material and how we have to, then we have to assess the performance in real time, followed by certification. In order to do that, selection, design, fabrication, and assessment and certifications, what do we need? We need a robust predictive framework that can establish the process, structure, property, performance relationship. So my entire research, we are focusing on this PSPP relationship only. But in this talk, I'm going to just discuss about the structure property relationship, how the constitutive model is playing my dominant role. Why do we need a microstructure sensitive constitutive model for that? That we talk about today. Why do we need a microstructure sensitive model? It's not a surprise to you for this audience because the second day and the last session. And when we take crystalline materials, the microstructure what we have, it is a hierarchical, multi-scale, and heterogeneous. That is very evident when I take an example of a welded configurations. We have a different microstructure in the weld zone, heat effector zone, and the base metal. So we have a features of a microstructure starting from point defects of vacancies, interstitials, all the way up to nanometer scale precipitates or sub-mesoscale, microscale level, subgrain boundaries, and then grain boundaries, and so on. So unless we know how to account for the features of these different microstructure and how they are affecting the performance of material, it's very difficult to capture the material behavior. So what I'm talking about the material behavior. In this talk, I'm confining myself into only mechanical behavior of materials. It means that very obviously we all know that whenever we talk about mechanical behavior, we have stress strain response. We have elastic regimes, and then we have plastic zones, followed by ultimate strain, then we have fracture. Okay, it may look like a more continuum scale, simple stress strain curve, but in reality, the inside the material, various deformation mechanisms are activating, starting from elastic deformation, followed by plastic deformation. The plastic deformation can come from glide mechanisms or tuning mechanisms or phase deformations and so on. And also, if you have higher temperatures or kind of environmental radiations, we may have a creep also. So these mechanisms play a dominant role, or these mechanisms actually governing whatever the mechanical response what we have in the material. Okay, in reality, what are the factors actually governing the deformation mechanisms? It depends on the loading. If I have a quasi-static loading or a shock loading or a creep or a fatigue, that depends on the loading condition. We have different mechanisms. And type of environment what we have, either temperature or irradiation, or type of microstructure what we have, and also other intrinsic property like a density, static for energy, all plays a dominant role on governing the activation of a deformation mechanisms. On the right hand side, I'm just showing a simple deformation mechanism map, like a simple representation of an ASB map, where in which we have a x-axis normalized temperature, y-axis normalized stress. Based on the combination of stress and temperature, we are activating different mechanisms, starting from elasticity all the way up to plasticity and the creep, either it is a dislocation creep or a diffusional creep. So if I say that, yes, the material is having a complex, heterogeneous, multi-scale microstructure, and we are activating various deformation mechanisms. Now, we need to have a robust or predictive model that accounts for both. In order to do that, what do we need? We need two things. One, a computationally efficient predictive modeling framework. Second, that framework supposed to have a mechanistic constitutive model that accounts for all possible deformation mechanisms, and also, very importantly, sensitive to the microstructure and the environment. So these two are the requirements for today. Okay, first I start with this framework what we have. So I always question myself into the mesoscale level or crystal plasticity modeling framework, because when I want to do the scale bridging, it is easy for me to span to continuum scale level or other around atom scale level easily. On both sides, we have 3 orders of dimensions scale, we have it. So in this case of crystal plasticity mesoscale model, it's of Sachs and Taylor, but I'm just showing a glimpse of it, only 4 models. That is viscoplastic silicon system model, that's very efficient and then effective model to predict the macroscopic response of a material, is a continuum scale model or effective medium model, I put that way. But that's not sufficient when I'm going to quantify the details of spatially resolved informations. Then we need to go for other models. I used to put 3 models. One is called Strata models, and then FEM based crystal plasticity model, and the last one is the Fourier transform based crystal plasticity model. But nevertheless, of different framework, in all of these frameworks, what are we solving? We are solving simple Euclidean equations along with the generalized Hooke's law, which relates the state of a stress to the elastic strain tensor using the term called anisotropic stiffness matrix, along with the macroscopic boundary conditions. So we can choose any framework, but what do we need now? How to establish this relationship, that is generalized Hooke's law. That is a place we are having, which is called the constitutive model. That constitutive model is supposed to be mechanistic, physics-based, and sensitive to the microstructure. We'll see how in our team, how are we developing the microsensitive constitutive model to establish this generalized Hooke's law. Okay, I start with generalized Hooke's law, where in which we have the stress tensor related to the elastic strain tensor. I put a superscript E to denote the elastic part, elastic strain tensor via this stiffness matrix. Now, we have to make an assumption here. Generally, in a continuum mechanics, we have 2 different classes. One is the infinitesimal strain approximation or the finite strain approximations. In this talk today, I'm going to confine myself into the infinitesimal strain approximations, wherein which the total strain what we impose to the material can be additively decomposed into elastic and plastic. With that assumption or approximations, we can rewrite this equation of a Hooke's law. Right now, the elastic strain tensor, this epsilon KLE, is replaced as the total strain tensor minus all the inelastic strain tensors or contribution what we're going to have. Very often, in crystalline materials, we may have a plastic strain due to glide mechanisms. There's a dislocation glide, plastic strain due to deformation tuning, plastic strain due to the phase transformations, the plastic strain due to dislocation flying process, and plastic strain due to the diffusion mechanisms. The climb and diffusion mechanisms very often activated at a higher temperatures and then lower stresses. But a glide, tuning, and phase changes can happen at room temperature to moderate temperatures, as well as low strain rate to high strain rate. So how to get it, all these things? So if I'm going to, in my venture research area, we are planning to build convoluted model for each one of them so that we can have a unified model that can work for a wide range of operating conditions. So today I just spend some time on only the glide mechanisms. For example, I start with this simple glide process. The glide strain tensor can be written in terms of a Schmidt tensor. M is a Schmidt tensor, and gamma naught is the shear rate of a particular dislocation type in a particular direction in a plane. Okay. So if I know the crystallography of the grain, I can able to calculate the Schmidt tensor easily. Then the question is only thing is how to get this gamma dot, which is the shear rate. Okay. The shear rate depends on what type of a slip we have it. Well, sometimes we have a materials homogeneous slip. It means that within a grain we have a uniform slip pattern. But very often we have something called heterogeneous or localized shear that leads to the shear and a deformation banding, something like this way. Okay. Doesn't matter of any way we have it, but we have to have more of mechanistic model that can capture for both homogeneous slip and the heterogeneous slip. For that reasons, what we do, we start with this simple RVE. We may have a microstructure, something like that. Then it will be represented in the model as a RVE model, or like a using a Voronoi tessellation, where we may build RVE microstructures. then it will be discretized. Then we have each and every material point, we have a called voxel. If I'm going to look at the voxel, the size of voxel may be in the order of a micron cube or submicron cube. If I'm going to look at the inside, we may have lots of complex dislocation structures. As a result of this complex heterogeneous dislocation structures, the stress within one voxel or a material point is not homogeneous. But thanks to nature, we can be able to approximate the stress state as a Gaussian distribution, something like that. Then we can write the probability for a stress distribution following this simple Gaussian distributions. Okay, so now the goal is to calculating what is the shear rate at each and every voxel. That can be written as simply an integration of shear rate at each and every sub-material point. Okay, we have a problem of how to calculate the plastic strain rate due to glide. That has been changed to how to get a shear rate. Now we said that the shear rate is not uniform in a given material point. Then we have to calculate the shear rate at each and every material point as an integration like this way. Now what we need to know what is the sub-material point shear rate, that is gamma dot. For that, we are using our own equations. What it says, very simply, it says that if I want to know what is the shear rate at some material point, that can be directly related to three physical quantities. One is the number of dislocation we have per unit area, or simply I can say the dislocation density along with its characteristics length, that is called Burgers vector, and what is the speed at which that particular dislocation is traveling for a given stress of a tau. So the Vs what we have, which is called a glide velocity. The glide velocity depends on the microstructure. Specifically, the glide velocity depends on the obstacles distribution and its interaction with the dislocation. Okay. Schematically, I'm going to show that one. Just imagine on the left image, we have a slip plane wherein which we have a different types of obstacles. I may have a types of like a precipitate type obstacle that is marked in the brown that circles, and we may have a different foreign atoms present at act as a solute distributions, that's blue ones, and we may have a dislocation junction also. All of these three can act as obstacles for a moving slip plane that is shown here. If I apply a stress, the slip plane may move, and these obstacles are going to interact with this dislocation line, and then the speed at which the slip plane can move depends on the type of obstacles and its interactions. So in nutshell, I can say the glide velocity of a dislocation at material point can be written as the distance traveled over the total time taken. Why I'm saying total time taken? For example, if a dislocation comes and meet an obstacle, it has to first bypass the obstacle before it can continue the travel. So there is a waiting time at each and every obstacle for a dislocation, plus the times taken to travel. As a result, I can say the total time is waiting time and the travel time. So now the problem has become that we need to find what is the effective mean free path we have. That's a numerator what we have lambda, and total time taken by a dislocation to travel. That includes both the traveling time and the waiting time. Okay, I can ask a question, how a dislocation can bypass an obstacle? It can bypass obstacles in two ways. One, just like a thermally induced vibrations related R1 looping mechanisms. Other one is climb assisted glide. For example, a dislocation can come here and seize an obstacle. The climbing process can help the dislocation to come out of the obstacle, then it can just continue. So these are two ways the dislocation can able to bypass these obstacles. So now the problem has been changed or has been shifted towards how to calculate the effective mean free path and traveling time and the waiting time. That we discuss it now. First I start with this mean interspacing. There's a lambda. That's the numerator what we have, the lambda. How to get it? Okay, we have various types of obstacles. As a result, we have to find the mean interspacing, which is obviously we always calculate using geometric mean concept. So as a result, 1 over lambda s, if I'm going to choose alpha equal to 1, I can say 1 over lambda s equal to the inverse of the lambda for all of these obstacles. What obstacles we have? The lambda rho s denotes the mean free path for the dislocation type obstacles. Lambda sg is this, the mean free path or between the subgrain boundaries, and then the lambda p corresponds to the mean free path between the precipitate type obstacles. We may have multiple precipitates. That's why I put like a summation over here, and then I have a I also in the subscript. Okay, so how to get, we have a Taylor's equation for all of these things. We can able to calculate all the mean free path distances on this numerator what we have here. Then next question is how to calculate this traveling time and the waiting time. Okay, the traveling time we can calculate it by using the wave speed at the in the solids. We can able to, by knowing the shear modulus and then mass density of the material, we can able to calculate traveling time. Then the waiting time. If I have only one type of obstacle, I can able to calculate how much time dislocation is going to wait at that obstacle. But if I have multiple types of obstacles, then we have to ask a question: what is the probability at which a particular dislocation sees one type of obstacle? Then we have to account for the probability while calculating the waiting time. So that's why we are calculating something called mean waiting time for a slip system like this way. So now we have a P rho or PP, which is the probability of a dislocation encountering a dislocation type obstacle or a prism type obstacles what we have here. Then in both terms, we have something called waiting time for obstacles. If I take a waiting time, here we are using a Cox activation enthalpy law, which calculates the waiting time for any obstacles by knowing this attack frequency nu and activation barrier delta G naught, that is the energy for activation barrier, and Kt is a Boltzmann constant, T is a temperature. Importantly, we have two terms. One is called what is the effective stress we have at the dislocation to bypass obstacle, and what is the critical strength we have here, which is often called as critical resolved shear stress, tau CS. In addition to that, we have two terms called P and Q. The P and Q denotes the shape of the obstacle profile what we have here. So now the problem is how to get all of these terms to calculate the waiting time. So the attack frequency we can able to calculate based on the type of obstacles what we have. Delta G naught we have to calibrate it, or we can do some kind of DFT simulations to get it. But now the question is what is tau effective and tau C, what we have, critical resolved shear stress, that we see it here. First, effective shear stress. What are the stress we apply? What are the stress we apply that is going to be resolved on the particular plane? That is called resolved shear stress, what we have in tau here. That has to be reduced by the back stresses. Here we are accounting for two types of back stress. One, the reduction or drag stress due to the diffusion of a solute atoms into dislocation core. That can reduce the amount of stress available for a dislocations to migrate. Second, the driving stress what we have for a dislocation that can be reduced due to the line tension of a dislocation. So these two terms can reduce the amount of stress what we have for dislocations to move. If I subtract these two guys from the applied stress tau, then we can able to calculate what is the effective shear stress available at a dislocation for a motion. Next question is the denominator guy. The denominator is the critical resolved shear tau CS. That depends on the what are all these strengthening mechanisms we have in the material. For example, it starts with the lattice friction tau naught. That's intrinsic lattice friction we have for every dislocation tau naught, followed by the strengthening due to the cell wall boundaries, strengthening due to the substitute atoms or the interstitial atoms, what we have solute strengthening, and then strengthening due to precipitates. So we have equations, thanks to all the scientists who developed all the equations, we have an expressions to account for or quantify the strengthening or the strength due to each type of obstacles, either from cell wall boundaries or solute atoms as well as the precipitates. So now we have all of these things into this one. Okay, next question, we can ask a question. Okay, is it a static calculation? No. Actually, when you do the deformation, the microstructure is going to evolve. What are things can evolve? What are defects what we have is going to evolve, right? Presently, we are focusing on the glide mechanisms. In the glide, the dislocation content is the main driving force. As a result, we have to account for what is the evolution law for dislocation densities. So if I'm going to consider what are the dislocations that is traveled within the cell interior, the rate of change in the cell interior dislocation depends on three terms. How much a dislocation can able to generate due to the plastic work, that's the first term, the generation term. Second, due to the temperature or other mechanisms or the dynamic processes, the dislocation can able to annihilate through a recovery term, that's called dynamic recovery, we have it. The third term what we have is called trapping or dislocation cell walls. Your dislocation can travel within the cell interior. If it encounters cell wall, it may be trapped. These are two ways in which your dislocation can able to reduce it number, or in addition to that, we can also generate also. So this is the way we can able to evolve or update the dislocation density what we have within the cell interior. For the cell wall dislocation density, whatever the amount of dislocation has been trapped at the cell wall from the cell interior, that will be as added to the cell wall dislocation density. But we do have sometimes the annihilation of a dislocation within the cell wall also. So we have to account for it. So this way, we can be able to update or evolve the content of dislocation what we have in the cell interior as well as the cell wall. So now I just showed a glimpse of it for dislocation glide, but we can do it similarly for all of these systems. Like how does the dislocation twin forms? That itself is a different topic, because the twinning is not going to happen just like there in glide mechanisms. It's more of a spatial dependent process. It starts with the nucleation process. The twin may nucleate very often at the grain boundaries. Then only a few twin embryos can able to grow. Then it can propagate, it can grow, it can able to thicken, or it can transmit. So that itself is completely different. Similarly for the phase change also, climb and diffusion. With the interest of time, I'm not going to go over each and every term in detail, but I sincerely request everyone to that, please look at various constitutive model development works from our team as well as other teams, what they have developed on various dissipative mechanisms of a plasticity. We have to account for all possible mechanisms that are, we have to move away from the Edisonian approach of trial and error, where which fitting some parameters. We have to go more towards the physics-based models. Then only we can be able to capture the effect of microstructure onto these material models. Okay, so now I just showed a only glimpse of what we have on the framework. So now I'm going to show only two case studies. With that framework, what can be done? First case study, I take it modeling of a slip banding, shear banding, or deformation banding. How one can be able to do that with this framework? First, what is a shear band? We all know that shear band is the very thin, narrow regime within a grain, wherein which the shear is localized, and also we have a significant change in the crystallography, crystal lattice orientation also. On the other hand, the deformation banding, wherein which we have lat-shaped regimes with significant lattice reorientation, but not much of a intense shear localization. So now I have developed a stack moments model with this constitutive model. Then we just apply it to predict what is the effect of a crystallographic orientation on the formation of this shear banding and the deformation banding. Okay, before that, why do we need this prediction? Is very important, because the shear bands very often act as a potential site for crack initiation and propagation, whereas the deformation banding, it helps to do the grain fragmentation. As a result, we have to predict what are all the microstructures, what are the grain orientations that leads to the formation of a shear band and a deformation band. So here, I just consider different most dominant texture what we have in a cubic materials, like alpha fiber, beta fiber, and then gamma tau fiber. And then we have predicted what are all the crystal orientation that can lead to the shear banding or deformation bandings. Here we have two measures. One is called the shear localization measure, which quantifies whether do we have any shear localization. Then lattice rotation measure, it quantifies whether do we have any significant lattice reorientations. If any crystal orientation, say here is a phi is an angle, one of the Bungay angle that shows the tau fiber variations. If any material point where in which we have both shear localization and then lattice rotation, then we named as a shear banding, wherein which we have only lattice rotation without shear localization, we call it deformation banding, wherein which we don't have both, which call the grain is deforming homogeneously. So we can be able to quantify what are the grain orientation that can lead to the formation of shear banding and deformation banding. So by following this approach, then later we have employed this fulfilled model to predict the slip band in a materials. So we have used the crystallograph-based phosphorate transform to predict these slip band formations in material. In addition to the formation, we have quantified what kind of a micromechanical stress and strain fields that may develop in the vicinity of a slip bands, which is really important because these stress fields are going to govern the continuing the slip banding, or it can act as a potential stress field for the crack initiations. So once if you have a framework to study, then we ask the question, okay, can we leverage the recent developments what we have in AI and ML community to optimize the microstructure? What do we need in order to prevent or delay or the formation of a slip banding? For that reasons, we have just used ML technique, wherein which we have used the physics-based model to build the data. From the data, by applying a neural network and then surrogate model development, we have optimized what is the best microstructure that can be able to minimize the formation of the slip banding. Or I would say not preventing it, it's only reducing it or kind of delaying the slip band formation. Or other words, I can say what is the best microstructure that can be able to have a lesser number of slip band or slip band chain formations. So these are all the ways we can be able to leverage the concept model what I have presented. That's the case study 1. Then if I go to case study 2, in which I have used the same framework of the advanced microstructure-based concept model to quantify the mechanical response under extreme conditions. So in this talk, I'm confining myself to only high temperature. So I'm going to study only the thermal creep response, but not on irradiation. But we do have results or kind of studies on how does the model can be leveraged to predict the irradiation creep, other mechanisms. How we do it? We start with simple microstructure. We may be able to get it from the experiments or from synthetic microstructures. Then we digitize it, and then we account for all the types of obstacles what we may have in microstructures, like a precipitate, solutes, and dissonant junctions. Then we try to solve any framework you can think of it, either VPSC or CPFEM or CPFMT, doesn't matter. We have to solve the equilibrium equations along with the conflict relationships. In this one, I'm considering anisotropic elasticity, inelastic deformation due to glide, climb, pinning, phase transformation, and vacancy diffusions. In order to make sure the framework what we develop, it is more robust and then unified framework, we applied for various boundary conditions, starting from constant stress or strain rate. Constant stress is kind of diode creep, constant strain rate, tensile deformation, and then compressive deformations, cyclic loading on a stress or a temperature, jump test on a stress and strain rate, in situ and ex situ irradiations. So these are the boundary conditions we have employed onto this framework to predict the response of various material systems, few steel alloys of austenitic stainless steel, and then ferritic martensitic steels, as well as the nickel-based alloys. So I'm going to show you a few results. What are the key results one can be able to get once if we have this so robust, sophisticated, robust model, what we have. Okay, I started some small results. One is the left-hand side, it shows the stress strain response of a material. It is 347H austenitic stainless steel, and the symbols are all corresponds to the experiment, and then solid lines from the model predictions. And here we have different colors corresponds to different temperatures. If you see it, the model captures the experiments very well. That is not much interest. What is interesting point? We all knew that if we increase the temperature, material is getting softer and softer. So if I see that 20 degrees Celsius at the top red, and then with the increasing temperature, the trend is going down. But if you look at it carefully, 550 is a pink and 650 is a black. Yes, at the beginning, with the increasing temperature, the strain goes down, but after 5 degrees Celsius, the curve goes up again. So why it is happening? So that cannot be rationalized without having the model what I have shown. It is due to the diffusion of the solute atoms into the dissolution core. That is a mechanism that actually governs this non-monotonous temperature dependence on the stress strain response, that we can able to capture correctly with this model what we develop. On the right hand side, it shows the thermal creep response for 2 different temperatures, and then for 7 degrees Celsius and 2 different stresses. How does the model capture this? But we can able to extend it for various stress and temperatures. These things are not much of interest apart from yes, model works well, but what can get a cool result? First key outcome, I would say, this is called synthetic deformation mechanism SNAPs. What I have here is x-axis temperature, y-axis stress, and here the color schemes tells you what is the steady state creep rate what we are going to have for various combinations of a stress and a temperature. If you're going to think of it, getting this kind of a large database on the creep responses from experiment is not possible today, because it may need huge resources, and also maybe like a few years to tens of years, maybe 10 years we need to build this database from the experimental. But since we have a mechanistic model that can be leveraged for a wide range of operating condition, here it means stress and temperature, we can be able to predict what is a creep data we are going to have for various stress and temperature combinations. In addition to that, in addition to color schemes, I have boundary lines. What is that one? Since in this model, we do allow for all different mechanisms, we actually track what mechanism is activated at what time, so we can able to see the relative contribution of different different mechanisms. For example, if I take a stress and temperature point here, in which if we look at it, that correspond to the temperature of 7 degrees Celsius and stress of 200 MPa, majority of deformation is glide dominated. Whereas if I take this point and which the stress is 20 MPa, the temperature is 600 degrees Celsius, it is mainly climb dominated. We can able to identify what is the dominant deformation mode is activated at each and every combination of stress and strain. It is nothing but similar to what we have in this kind of acid deformation mechanism there. But now we know to perform hundreds of experiments for longer duration, like years of time. We can able to use this map data or this model to build not only the three-plate response file, and also we can able to build something called deformation mechanisms map, similar to what we have in a Ashby-Whitman map. That is one of the key outcome we can able to get from this modeling approach. Second, what we can do with apart from that, okay, very often we may have one material, and to improve the performance, we may do some kind of a heat treatment or some kind of a thermomechanical processing, we may do it. In this case, I'm taking a heat treatment. For example, I'm starting with a base microstructure in which it has this cell interior dispersion density of this much and cell wall of something, and then it has the MX type precipitates, and we know what is the number density and size of the precipitates. For this given microstructure, we can able to, sorry for that. Okay. So for this given microstructure, we can able to predict what is the creep response for a wide range of stress and temperature. All fine. All fine. Now we are asking a question. Okay, we are starting from this microstructure. If at all we do kind of any heat treatment, here we are applying a aging process. If I do the aging process to it, what's going to happen? It slightly varies the content of microstructure what we have, as well as the primary MX type precipitates. But in addition to that, the aging process introduces the secondary precipitate also, like an iron carbide precipitate. We have a second type also. Fine. So now we have this new microstructure. We can able to perform the same simulation. The entire simulation took only like a maximum of 3 days. We can able to perform creep simulations to cover primary, secondary, and all for various stress and temperatures easily. But now, interesting point what we get. In addition to capturing the effect of aging process, we can able to quantify what is the effect of the aging process induced secondary NBC precipitates on creep rate as a function of stress and temperature. What do we all expect it? Whenever we have more precipitates, we can expect a strengthening mechanisms. As a result, we can expect the reduction in the creep rate. But it's not the case. If I'm going to calculate change in a creep rate with respect to the of case 2 with respect to case 1, if you see it, we have both positive and negative. It means that what? The effect of secondary precipitate is not uniform in the stress and temperature space. For a given combination of a stress and temperature, we may have some microstructures beneficiary, but the same microstructure may not be good for other combinations of stress and temperature also. That we can able to get this kind of information from this kind of a framework. Okay, one more thing, what we can do with that one. Understanding or quantifying the effect of a chemistry of the material systems. This is really a pathway to design the alloy. Here, I took a 347H stainless steel material, and then I'm just slightly varying the chromium content within the regimes wherein which we can retain the same structure of the crystal. Then we can able to quantify how does the chromium content plays a role on the creep response of materials. So this way, we can able to now play slightly, or we can able to optimize the every element what we have on the alloy compositions to quantify its response on the final material behavior in the real time. One more application I just thought of it. Okay, how we can able to use this framework to optimize the manufacturing process and then to quantify the final response. So very often in real time, what are the material we have it that undergoes metal forming process followed by heat treatment. So we may have hot or a cold rolling or a forging or extrusion, something like that, followed by a annealing, aging, normalizing a temperature, something we can do that. So what we have done, we have used our framework to simulate the metal forming process as well as the heat treatment. By doing that, I have generated 900 different processing routes. For example, a hot rolling followed by annealing, or forging followed by aging, or extrusion followed by annealing and then aging, something like that, different manufacturing routes. Then we got 900 different microstructures from that. So if I'm going to simplify all in a database, we can able to put that into range of different microstructures to encompasses various metal forming as well as the heat treatment processes. Now, I'm asking a question. Okay, now I have a 900 different processing routes that leads to 900 different microstructures. What is the effect of this microstructure on the material response? Same alloy, same composition, nothing changes. Only the manufacturing route has been slightly changed, very minor changes. As a result, what we see on the performance. Here, I'm just showing the model predicted the steady state creep rate as a function of a stress for a given temperature, say 600 Celsius. The three different colors correspond to three different grain sizes, and the span, the range what we have for every stress, it is due to different microstructures. If you see it, the creep rate what we predict from the model or whatever model suggests that it is not a very narrow range. We have several orders of variation. We may going to have a creep rate as a function of the microstructures. Very often people try to go for a material selection based on the what they want performance. But now what we are saying from this one is your creep rate can vary several orders of magnitude by slightly changing your manufacturing process route. With this work, what are things we are concluding? Yes, the destruction density, precipitate defects are playing a major role compared to other things. Grain size also play a major role, particularly in the low stress regimes. More importantly, the symbols what I have, these are data from different literatures. We can say that, okay, from group to group, we may have variation. But I'm going to consider only one group that is called NIMS database from Japan. That is circle one. If you look at it carefully, we have a large variation in the creep responses from the same group. Why is it so? That is, we can able to explain or rationalize now, even we have a slight differences in the initial microstructure for samples, we may going to have a significant variation in the material response at the end of the day. So that can be rationalized with this kind of approach. Okay, so now once if you have that one, it's an RVE level. Is it that's it? No. We can able to go for a component level simulations. How we can do that? If you're going to do the brute force way of a scale bridging, that is good to some extent, but it's not always convenient on several factors. One of the factor is the computational intensity. So for that reason, we have used machine learning to bridge the length scales. What we do? We build huge database of material responses by performing the polycrystal level mesoscale simulations, and then derive a surrogate model with that, and then just use surrogate model as the constitutive equations. So at the beginning, I was talking about we need to have a constitutive model which is sensitive to the microstructure. Yes, here also the ML based constitutive model which is sensitive to the microstructure, but it has been integrated into FEM so that we can able to capture the material performance very well. So these are all the ways we can able to use once if you have a mechanistic physics-based constitutive model in place. Okay, I'm showing simple example of welding simulations. I'll skip this one. So what are we doing in our group? Our laboratory is called Computational Mechanics, Materials and Manufacturing Laboratory. In our group, our goal is to develop a digital twin to establish this pre-SPP relationship. For that, we are doing two ways. One is called virtual processing, other is called virtual characterizations. Right now, we have done so far on the glide, climb, all this kind of physical metallurgy or material science aspects. Right now, we are extending our framework to account for multi-physics, like something called corrosion, solidifications, thermal model, chemical diffusions, fraction and all, we are extending it. So this is all the work we are doing in our group, and we have a few, I may take this opportunity to share with you all, because we have some students here. We have few openings in our team to work on various projects. So if you're interested, please reach out to us. So with this, I'll just end my presentation here. If you have any questions, I'm happy to address and discuss with you right now, but you can reach out to me in this email address also. I stop here. If you have any questions, you can raise it. I'm sorry for that. I know I'm traveling. We have lots of noises at the back. I'm sorry for that.
So it was a very nice presentation, Arul. We are so grateful that you even at your You are traveling.
I think you are muted.
We are muted.
Oh yeah, now I can hear you. Yes.
Yeah. So thank you so much, Professor Arul, that you took your time from your busy schedule, right? You're traveling now, and still you gave such a outstanding presentation. Relationship with crystal plasticity and texture, and relations to hardening mechanism, and it's very important to understand, right? And microstructural variations, formation of these constitutive model and all, and different kinds of hardening phenomena as you described. Should be very useful to these students. I would really like the students should have some question. Yes.
Good afternoon, sir.
Hi, good afternoon.
Sir, how you decide the input parameters that goes into the crystal plasticity simulations that you are performing? I mean, do you tune it with some experimental data, or you take it from literature, or from atomistic simulations and all those things you find out?
Okay, yeah. So it is one of the open challenging problems who are doing modeling that we have it for long-standing issue. And the way we do it, we classify the material property and then parameters separate. Property, we can get it from these low-level scale calculation or some experiments. But parameters, model-specific parameters, we often confine it or find a range from the low-level scale calculations by performing a DFT and MD simulations. And then on top of it, we use some basic SQL data to parameterize it. For example, when before going for a creep data, if you do some kind of stress relaxation experiments, we can able to parameterize various terms in these equations. We use both lower length scale calculations and then the experiments to parameterize these equations, what we have. Yes.
Okay, sir.
Sir, in calculating velocity, you are taking waiting time plus the traveling time. So
yes.
Why there is a waiting time?
Okay. So if a dislocation just traveling, if it meets an obstacle, it has to bypass obstacle. It cannot just shear through. If you have a shear through obstacles, then shear through. But even then, it has to bypass. The bypass mechanism is different. It takes its own time to bypass obstacle. That time we are taking as a waiting time. But not only if you have a clean slate, then it's just shears through, just a travels it. Then it is different story. Since our materials have a lots of heterogeneous microstructure, we have to account for the waiting time at the obstacles.
Okay. So that.
Very good lecture, sir. So I would like to ask this thing that you talked about this velocity, right? So that you did by distance by time. So can I take it that this like this thing follows Newtonian mechanics, or like there is something else?
No, if you want to, okay, if you go and switch to the mechanics side, yes, still we are doing the Newtonian mechanics and continuum theory. We are not going with any non-Newtonian or discrete. Still, it's a continuum Newtonian mechanics only. We are doing it.
Okay.
And then I'm not tracing individual dislocations here. It's a collective dislocation slip line only. I'm talking about it here. It is not a discrete dislocation. It is still a continuum mechanics based approach.
Okay, sir. Thank you.
Any more questions?
Hi, Arul. Very nice presentation that you gave. Very involved, very in depth in a lot of issues. So you glossed over many things, of course.
Thanks.
Yeah. It's great work that you do, of course. I have a lot of questions about some of the assumptions that are made to go into the model? And
Yes, please.
in the philosophy of your laboratory, where you're talking about virtual manufacturing and virtual experiments, so you're relying on the, you're relying on the simulations to get you the information that you're using in your machine learning algorithms, right? And
Yes.
and so, the verification, the validation of some of those becomes very important, and I'm just curious how you're doing that part of your analysis.
Okay, I agree. Yes, the verification validation is a challenging and more important part of the framework development. So the way I'm doing it, building a small blocks of the framework, not at a single go. Everything is developing in one single go. For example, if I'm going to do anything on additive manufacturing, before jumping into additive manufacturing framework, I do simple annealing process, solidification process, and then welding simulations. So those small heat treatment processes or welding simulation, we do it, and then we do the experiments, and then validate it, build the model. Once those puzzles, small piece of puzzle is ready, then we integrate it. Then we perform the complex experiments. So it is more hands-on-hand with the experiment and model development. And yes, I agree, it's not simply we can do one-to-one mapping sometimes, and we have to make some assumptions. And for those assumptions, we perform some low level scale calculation, either using a DFT or MD, to validate or prove or disprove whether our hypothesis or the assumption is valid or not. So it is like a continuous process of building small blocks and then integrating it. That's why I'm doing it. But what are the goal I am right now putting it? Maybe that's my vision or my long-term plan. And so far, I would say we have a reasonable core on the virtual characterization. Right now, I am doing on the virtual processing. Successfully, I have completed for the welding and other metal forming processes. Right now, we are in maturing stage on the additive manufacturing. So we have to integrate everything. Then only I can say it's a digital twin platform for all. Yes.
Yeah, very, very nice work. Thanks.
And I'd like to thank you for, I can see you now. I think I met you at TMS way back in San Diego. I think several years back, I think 3 years back or 4 years back, I met you. So it's good to see you here. Thanks for visiting India.
Thank you. Always nice to be here.
Yes, thanks.
So thank you so much, Arul.
Yeah. And maybe I'll take a minute, and I'm really sorry for all the noises what you're all hearing. And I'm in Tamil Nadu, this week is Makara Sankranti and Pongal holidays, full noise and everything. I'm also traveling. I'm sorry for all the noises and everything. So I hope some other times we can have more relaxed discussion and then calm presentation. I'm sorry for all the disturbances.
No, we didn't get the disturbances actually. We enjoyed your presentation. We have a small gift for you, as because you have done this online. We'll send that to you to IIITDM Kanchipuram by post.
Okay, thank you. No worries. Thank you so much.
Thank you, Arul. Yeah. This was your last talk of this entire symposium, and then you may log off and carry on with your travel. See you then. So, session ended, and this was the last session of this symposium on texture in material. You saw the different facets of texture, and you can see that though texture as a parameter of physical metallurgy covers many aspects, like for example it covers crystallography. Definitely you should know crystallography, and then it is related to mechanical metallurgy, definitely then, right? So if it is related to mechanical metallurgy, then it is somewhat related to applied mechanics also. So you have these constitutive equations which you have to have knowledge of applied mechanics to solve them. So what we can understand, that when we talk about microstructure and texture, texture is one way of quantifying the microstructure, entirely polycrystalline material, and polycrystalline material I don't think cannot be described microstructurally without considering this thing which is called texture. Now, when we call texture, then that means it's something in mathematics, right? Like, for example, as Professor Satyam Shua said, it can be described by 3 angles, Euler angles, phi 1, phi 2. So it's a relationship between the sample reference system and the crystal reference system, where you know that we actually rotate the sample reference system to the crystal reference system for every crystal that is present in the polycrystal, right? So now, deformation simulations are one of the things which can be used to relate the, you know, the critical resolved shear stress ratio of different slip systems present in the material and relate it to the stress strain curve, basically. The stress strain curve of any material, say for example a tensile test or a compression test, right? And then it gives us an idea to that what kind of, if we know the slip systems, right? So which slip system is more, which slip system is less, depending upon, of course it is more complicated than what I am saying. And then you can know the activities of them. So which one is going more, which one is going less. And based upon using those things, we can determine the, you know, the texture of the material by just mathematically. And though there are lots of assumption of doing that, and it may not be exactly what is happening in the real life scenario in deformation of a real material, but still we can get very good answers. We can get very nice information about how the internal deformation is going on inside the material and all. So I will keep this up to now, up to this, so that what I said and they said be there in your mind and let you think that what you are doing, what research you are doing, can you relate it with these things? And if you can, please use it. Okay? Thank you so much. So we will have a small valedictory session. Okay, nothing much. Okay, but just we should wait for some time. There should be a coffee break now, right? So after that, we'll come back as a valedictory session, and within 5 p.m., we'll just get dispersed. Coffee? Is there?
হ্যালো হ্যালো হ্যালো, জোরে দেবেন। হ্যালো 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 হ্যালো, আর বাড়ানো যাবে না?
হ্যালো।
এই হাসছো কেন গো, হাসছো কেন?
হ্যাঁ, হ্যালো 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 হ্যালো।
সে লাস্টে তাহলে
হ্যাঁ কিছুক্ষণ পরে 10-15 মিনিট
হয়ে গেল।
আবার কি এই তো হলো আবার কি
ও
হ্যাঁ আর তুমি কিছু বলবে
গাইতে হবে না?
গাইবে
ও বাবা, এই কি কেউ আর ডিরেক্টর আসবে না? হ্যালো হ্যালো, হ্যাঁ এটা ঠিক আছে, কিন্তু এটা হ্যালো, এটা জোরে হ্যালো হ্যালো হ্যালো, এটা তো এটা এটার মতো জোর করুন না। হ্যালো 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 হ্যালো, 1 2 3 4 5 6 7 8 9 10, ওকে ঠিক আছে। হ্যাঁ কি বলছো? অফ কোথায়?
उसको ना थोड़ा सजा दे ताकि वो लोग यहाँ से आके ले जा सकें। कैसे लेगा? हाँ हाँ, वो टाइम है। मुश्किल है, अच्छा ना। So we have come to the valedictory session now, and we will not we will not talk a lot of things here. We will finish it off as early as possible. We have our, dinner here in packets. We have souvenir for all of you, and that's the T-shirt. You can show. Show. No, don't show that. No, don't show that. Black is not good. Show the original one. Yes. Yes. So it's not pink. If you are looking pink, then you won't get it. Yes, I got it. So let us finish up this valedictory session thanking Professor David P. Field, who has come a long way from Washington State University. So I think from Washington State University you have to came to Seattle, right? You came to Spokane, okay. And from Spokane, you drive to Spokane, right? And from Spokane to?
This time I flew to Salt Lake.
Spokane to Salt Lake City. And then from Salt Lake City to Heathrow Airport, London, right? And then from there to Bangalore. And from Bangalore to Calcutta. And from Calcutta to Kharagpur. So it was a very long travel. We will ourselves think about a lot before we start such kind of a trip, right? It's a long trip. So we should give another applause for him. He came here for the second time in the SPARC, in the same SPARC, and in the initial SPARC program, he was with Professor Sinisa Mesarovic and Professor Shomik Banerjee, also from WSU. And we had a 2-week long workshop on texture and triple junctions. And we tried to understand there that how we can use phase field modeling and molecular dynamic simulations to solve the issue of this phase field. This time, we have made it into a small symposium. In that, we had Professor Field, Sinisa, and Shomik as the speaker. It was too rigorous for them. And I'm very grateful that they didn't say a word. They did like the hard task with smiling face. So I'm very grateful to all three of you for that. So I wanted to call all of them, but the SPARC we got is for 4 trips only. So we could only manage to get back Professor Field, who is also the PI of this project along with us. So here myself and Professor Shampaj and from WSU, all the three of them. Though we have to do a lot of things, I would like to announce that whatever we have presented here in this symposium is we are trying to bring it up as a book, a collection of work relating to crystallography, texture, grain boundary and triple junctions. let's see whether we can publish this in Springer. We will try for it. I think we will be able to. And with that, I would like to say that Professor Field is here up to, your flight is on 24th morning, right? Afternoon. So he is here up to 23rd. So if you have any issues with understanding microstructure, or even if you have any issues or questions regarding publications, because Professor Field is a highly experienced person, a highly experienced researcher, and he has worked in various aspects. He was in your shoes some 30 years ago, right? Now, presently he is also the I'm not sending you back, don't worry. Presently, he is the editor of chief of editors of Materials Characterization Journal also. So you must be able to know that what we must do or what we must not do for any publication, if you have any question. Okay. So yes, but yes, please don't bug him too much, because he is also a human being like us, so he has also limited time. They're told not to move away from the dais. So yes, but he is, yes.
If you're bugging me, I'll tell you go away. Don't ask questions if I can't take it. I'll just say go away.
So before we end this session, a very important task that Professor Shompage actually agreed to do, and this is the end of the valedictory session. Only after your small singing song, okay, Professor Field, if he likes, he will say a few words, and that's it. It will end our session with the distribution of the souvenir and the food packets, right? So I won't speak anything more. Students will laugh, then that's their problem. Please come. She is shy, but I requested her to sing a classical song for us, because I heard her while she was singing once. I didn't expected that she could sing so nicely. So actually she is a practiced singer. And she is very shy to express that very nice ability in front of others. Yes, that's why she is saying that they will laugh at me, or nothing will happen. Please come.
Okay, so nice introduction, but I'm not sure whether I'll be able to hold these words. So. Okay, hello. So, as I'm a teacher here, so little bit trend is like that to teach the students, okay. So, I will start in that way. This is a valedictory. Professor Biswas already did that valedictory session. I will give little bit different flavor or a sense that is based on music, songs, okay. So, this is based on mainly Hindustani classical music based some song. I'll sing couple of songs. So based on Hindustani classical music, that is eastern part of the world. So, but western side of the world, that is for Professor David Field. So he might not be able to understand nicely because he is not very familiar with the Eastern region culture and mainly the songs they deliver. He is used to listen the Western songs, but the basis is same. Okay, this is little bit educational background. Like for the eastern part of the world, we have 7 notes or tones for basic tones for the song, vocal song. But at the western part also, they have the same 7 notes. The basic tones are same. Okay. As for example, I'm just trying to sing that. The eastern part, okay, I have no instrument, but I have a tanpura in my mobile, so I can play that. Can you hear this sound? So this is the 3 main tunes are playing here. Sa, pa, pa, sa. These 3 tunes. না না এটা আমার লাগবে তো So here in eastern part of the world, the 7 tunes how we sing. Sa re ga ma pa dha ni sa. Sa re ga ma pa dha ni. Ascending, descending, sa ni dha pa ma ga re sa. That is in eastern part. And in your country, how people sing? Do re mi fa sol la ti do. Ascending and descending. Do ti la so fa mi re do. Basic tunes are same. Only the vocabularies or words are different. One is singing sa re ga ma pa dha ni sa, sa ni da pa ma ga re sa. Then you are singing do re mi fa sol la ti do, and the opposite way. Okay. Now the eastern side composed their song based on these sa re ga ma pa dha ni. They have put color, they have put ornaments, everything. Whereas western side based on that do re mi fa sol la ti. Okay, the tunes are same. So that is the major connection between eastern part of the world and western part of the world. Okay, now hello, I will sing 2 songs. First one is based on khambas, rag khambas. Maybe many of you are not very familiar with that. So this is one of the raga in Hindustani classical music. There are many ragas, so this is one of them. And I will sing a song bhajan based on that. But before that, I will give little bit essence, bistar of that rag, how it is. Saga saga of khambas. Okay. Now, based on that, I will sing a song. It is a bhajan, very well-known bhajan. That was originally sang by our beloved Nightingale, Lata Mangeshkar ji. You know, she is late now, but she is eternal, right? So that Vaishnava Janato. And it is a big bhajan, so I have cut it in half of that. Long time no practice, maybe so her voice will crack. So वैष्णव जन तो तेने कहे जे पीड़ पराई जाने रे वैष्णव जन तो तेने कहे जे पीड़ पराई जाने रे पर दुखे उपकार करे तो है मन अभिमान ना जाने रे पर दुखे उपकार करे तो है मन अभिमान ना आने रे वैष्णव जन तो तेने कहे जे पीड़ पराई जाने रे सकल लोकों साहुने बंदे निंदा न करे के नीरे सकल लोकों साहुने बंदे निंदा न करे के नीरे वाच काच मन निश्चल राखे धन धन जननी तेनी रे वैष्णव जन तो तेने कहे जे पीड़ पराई जाने रे साम दृष्टि ने तृष्णा त्यागे पर स्त्री माते जेनो रे साम दृष्टि ने तृष्णा त्यागे पर स्त्री जेनो मात रे जीवा था कि असत न बोले पर धन झाले हाथ रे वैष्णव जन तो तेने कहे जे पीर पराई जाने रे पर दुखे उपकार करे तो है मन अभिमान नाराने रे वैष्णव जन तो तेने कहे जे पीर पराई जाने रे वैष्णव जन तो तेने कहे जे पीर पराई जाने रे Okay, so thank you. And the second song, that is very well known and common, everybody knows that. Okay. So that is a patriotic song. I chosen that because this is a conference and it will be very nice. As Professor Field is here, he is from foreign country, and he also will be familiar with our patriotic song that is written by Bankim Chandra Chattopadhyay, and it is on any patriotic occasion we sing this to pay respect to our country, Deshmatrika, India. Okay, that's Bande Mataram. And I mean, incidentally, this Bande Mataram is also based on a similar rag Desh, you know, because the composer who has composed the tune of this song, because it is a patriotic song, he has chosen the basic tune from that rag, which is called Desh. It will be matching Desh from rag Desh Matrik song. Okay. And it is almost similar as Khambaj, the thought is same, but it's little bit modified tune. So I am singing that. If you want, you also can sing with me, because everybody knows that. Okay. Vande Mataram, Vande Mataram. Again. Vande Mataram, Vande Mataram. Sujalam, Sufalam, Malayaj Sheetalam. Again. Sujalam, Sufalam, Malayaj Sheetalam. Sasya Shamalam Mataram, Vande Mataram. Shuvrayatsna Pulakitayaminim, Fullakusamita Drumudala Sobhinim. Shuvrayatsna Pulakitayaminim, Fullakusamita Drumudala Sobhinim. Suhasinim, Sumadhuravasinim. Again. Suhasinim, Sumadhuravasinim. Sukadang Varadang Mataram, Vande Mataram, Vande Mataram, Vande Mataram. Thank you. And last but not the least, couple of sentences that maybe you are thinking, hey, this is metallurgic and materials engineering department. So what is the point of singing music and all this? There is no relation. But ironically, you know, there is a strong relation. Do you know what is the relation? Now, all words start with the same letter. Metallurgy, materials, music, all starts with M. So triple M. That's it, the major connection. Namaste. Thank you.
So it was really beautiful, right? So I would ask Professor Field if you would like to say something at the end of this ceremony. Yes.
Okay, Shampa, thank you very much. That's courage. It takes courage to do that. So thank you very much. So is that the national anthem from India? Is that national song? I have in my office a book of poems by Tagore, Rabindranath. And all my Indian friends that come in always say, "Oh, he wrote the national anthem." So that's a different song, yeah? Okay. 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 Okay, I won't sing anyway, so that's okay. I'll spare you. Anyway, so thank you very much for being wonderful hosts. It's great to be able to interact, especially in talking about texture with everybody who's learning about texture. That's the funnest part of being from the prior generation. The funnest part is to see the new generation learning about texture and doing great work. I mean, one of my favorite things is to be a cheerleader for my students, right? I see they bring me great ideas. I'm like, wow, I never thought of something like that. And so I love seeing that, and I love hearing your ideas, and please keep coming up and talking to me. I'll be here another week or 10 days or whatever from now. And so I'm happy to continue to interact, and emails, later, feel free to email me and connect. So that's fantastic. I think I've mentioned to several people that texture kind of grew out of Germany. I think Satyam mentioned that it grew out of Germany, texture analysis generally. And that was kind of the bed of texture in the late 80s when I started working on texture. But India is one of the main places now where you study texture. Some of the best texture experts in the world are here in India, and we've heard from several of them, which is fantastic. And so I've really appreciated being part of this meeting and this symposium. So thank you for the organization, to Somjit and Champa, and for all of you for your participation. Thanks.
So we came to the end of this session. Okay, so the valedictory session has ended. Now what we need to do is that we have some souvenirs for you, and we have the dinner for you. So I would ask Sujit and Gaurav to call up their names, and I think I would task Professor Sampaij. She will keep sitting there, and to give the T-shirt one by one, and the food packets, Gaurav, and the lychees maybe to the students one by one by Somudev. Okay, can you do that?
एक एक करके नाम बोला। अच्छा, एक एक करके, हाँ, तो तब भी टिक लगा सकते हैं।
सर ये भारी होगा बहुत। हाँ। अरे इन लोग बोला था ना, एक एक करके इस रो से बोलते हैं जल्दी।